Hey guys, today we'll be talking about spring break, but with less break. Now, let's say that you're bungee jumping. You're with your friends, you want to jump off the cliff with them, but then a crocodile at the bottom says, "Yum yum, delicious," and then they eat you because you didn't complete the lap correctly. In reality, though, we're in an oscillating universe with realities that should bend and shape around us, like the electrons, the Earth around the sun, uh, and especially this lab. So, as engineers, it's important that you understand this balancing act exercise, where you have to understand that one force has to counteract the other. And that's the thought that we're going to lead into for the implementing principles in today's experiment. We'll be talking about the energy principle, Hooke's law, and momentum principle, and we'll get to see more of that zeroing out in just a second with the visual code. But let's get back to the topic right now. From 1 to 3, energy principle. Energy in is equal to energy out, pretty much. You could have different forms of that energy, as we'll see, but as for the actual quantitative numbers, they're going to equal out to 0. When I do Hooke's law, it says that for any displacement, there's some kind of spring constant that's multiplied by it in the opposite direction of the force applied, and that's going to be my force. Potential energy is just the derivative dx of that distance that we're talking about, that x from before, and this one will just be the potential energy, which is, again, related to your energy principle. The momentum principle is the net force change of the object's motion. So, as we'll see from the spring and mass counteractions of the moving object, it'll look a lot like a balancing act between the momentum principle, spring, and the gravity. So here's a progression we'll go in. We'll observe the ball and spring falls. We'll get some math for the constants. Then we'll plug those into computations for the VLab, and then we'll get final results and questions. So here we could see from the tracker video that as a ball oscillates around, it creates an oscillating graph like a sinusoidal wave, as a spring should. And over there, we're going to plug in our data. So again, it's the momentum principle. They're oscillating each other, and we're exporting the data. Here are oscillation times. Here we could see that the x is dependent on gravity, and that the y oscillation times is dependent on the spring constant, or aka that tension. So let's think about y. So let's say that we have two scenarios. So the ball on the left is being suspended by a string upwards, and it's not going to be moving. It might be oscillating by a spring up and down, thus relying on that tension, but it's not oscillating left and right. If for it to be oscillating left and right, it has to actually be tilted like so on the image on the right. Thus we could say that gravity is depending on the x, and that the tension forces are depending on the y, or vice versa. And now let's quickly solve for the spring constant and relaxed length. So given that time is equal to some kind of inverse proportion to that angular velocity, then we could say that if we know that negative kx equals mass times acceleration, then we could solve for that angular velocity to then get angular velocity squared is equal to the spring constant divided by mass. Now when I relate those top two right formulas together, I could solve for the spring constant once I rearrange it for things that we know, such as the oscillation time and mass. When I do that, I'll get 6.87 Newton meters. And substituting in negative m or negative kx is equal to mass times acceleration, then I could solve for that x, which is that change in length. Now given that our max length is given, and I subtract that from something else that we just solved for, which is that change in x, then I get L naught, which is 0.127 meters. Now it's time for some coding. Let's go. So here we define our energy predictions on the columns that is shown. There is a bit of Hooke's law, if you could see down in the below and highlighted, where we have that potential energy that's related to Hooke's law. Here we have the Hooke's law forces and Hooke's law displacements being shown in the highlighted blue arrows. And in the light blue, we have the momentum principle, where we see that spring and gravity are trying to counteract each other to give that overall motion of the ball from a non-constant velocity. Here we could see, as I import that data from before, from the experiment, we could see that the delta E, delta energy, total energy is equal to 0. It's that orange line that we see. And we see that the model and experiment are lining up relatively closely. There's a slight margin of error. Now, something to note is that forces are in constant counteraction, hence that oscillating graph, and x and y in counteracting oscillations, where one would counteract the others, as shown in that graph. So, for your model system, is the energy principle satisfied? Justify your answer by discussing briefly your parts of energy changes. And the answer is that, yeah, the energy total is equal to 0. We can see all the energies, the delta K, delta grav, and delta spring are all, well, totaling out to 0. Here in the oscillating time, we have to tell what our x and y positions are going to be dependent on, compare the two estimates, and then discuss the differences between the two. Well, we could see that the x oscillation period is just ever so slightly longer than the y oscillating period, and this is because the x depends on the gravity, while the y oscillations depend on the spring constant. Right, that is all. See you guys later.